Okay, welcome back for the morning. Good morning before next week's PE. Just want to remind everybody, next week we have our PE. Okay, that's very important. I already mentioned most of the details yesterday. I don't want to repeat it, but please read through the instruction. There is a click here. There's a click here that please remember to read through the instruction there. Get yourself well prepared. The most important thing is you're going to use our lab PC to not lock out the PC. And two important things. One is you need to remember your cosmology password and log in because you need to log in from scratch. The other thing is during the PE to not close your PE cosmology page. That is a check. We will actually use it that makes sure you are only on the PE cosmology page. That means you cannot go to other cosmology page. You can not go to any other page anyway. So you cannot go to any other page. For example, you cannot go to even our own course to access our material. You cannot go to our other course to leave comment, communicate, whatever, because they will all be recorded and cosmology will actually feedback to our invigilators to know that you are doing something funny. Okay, we have a monitor to monitor every computer. What are they doing? If you are doing something funny, we will send the invigilator to go and talk to you. Okay, so please do not do anything funny, and please read the instruction. Okay, today we are going to talk about SSSP. Okay, what is SSSP? SSSP stands for Single Source Shortest Path Problem. Before explaining, I think we all are very familiar with this. Like Google Map, whenever you don't know where to go, you use Google Map to find your place, right? For example, I'm in NUS. Now let's say we're in NUS Comfrey. Okay, that is where we are. And then what happened is I want to go for direction. Where do you want to go? Let's go to airport. 乘一九. Okay, let's go to 9. And then what happened is you can ask. So Google Map will find you the shortest route. Okay, shortest route as in Google Map probably is the time. So this one is for driving, and of course you can find public transport. This is the map for public transport. So Google Maps suggests you take a bus to Clementi and all the way ride the MRT to airport. Okay, so that is what you do on Google Map to search for shortest path. The question is, how do you do that? So that's what we are going to talk about today. But wait, you say, there's different shortest path. How do Google Map do it? Actually, very simple. Google Map do it on different maps. For example, if you want to find public transport, Google Map only use the public transport map. If you want to find walking, you can walk 7 hours from the airport. Okay, you find use the map that you can walk. If you want to just drive, Google Map will find you a car driving route. So just need to use different maps. But the question is, how do you find the path? That's what we talk about. And one more description is in Google Map, actually it's slightly another problem. Google Map is doing single source, single destination, shortest path. It's okay? That means I actually have one single source. I want to go to one single destination and I want to find the path. That's what Google Map do. But today, what we're going to do is single source, shortest path. That means our algorithm today can find one single source to all the nodes. What are all the shortest paths? That is what the goal. And Of course, there's another algorithm called multi-sources, multi-sources path. But there's another story, okay? We are not going to mention it in our course. I want you to note what today's goal is, single sources path. But before that, we'll talk about one algorithm called Bellman fault. Just a summary for Bellman fault. Bellman fault is going to be slow. It's a slow algorithm. Tomorrow, next week, we'll talk about another faster way, which usually people do. It's called Dijkstra. However, Bellman fault has its very important role. There's something Bellman fault can do, Dijkstra cannot do. Okay, if it's left there, even it's low, it's left there alive for a reason. There's a few features Bellman fault can do, Dijkstra cannot do. But also, the other important reason why we introduced Bellman fault is there's an important operation in Bellman fault, which is the same as Dijkstra. And that one usually student is something like probability. Some students understand. Some people don't understand. Itself is a very simple algorithm. You know something in life is like that. Something you understand. You don't understand. Okay, so the relaxation process for some students is a piece of cake because it's very simple. Actually, it's very simple. But for some students, don't know why it's very difficult to understand. Okay, so I try to get through the relaxation on here. Okay, for example, we just introduced, we want to find the shortest path. So in a map, the map you know that actually can be so-called modeled as a graph, right? So in a map, I want a single source. I want to find the shortest path. And usually you can find a Google map. So how are we going to model the graph? First of all, yesterday we talked about a graph can be directed. So what we want to do is we want to treat our graph as directed graph. You say, how do you do undirected graph? Very easy lah. For undirected graph, that means every undirected edge is a two-way edge. I just replace the undirected edge to double direction edge, okay? So undirected graph is also okay. However, there's one more extra augmentation for the graph. Each edge has a cost. That means if you want to use that, you want to travel through that edge, you have to pay a price. The price is an integer. And I want to warn you first, this weight may not necessarily be positive integer. Okay, that was what we are going to deal with a serious problem. That means, for example, if I want to go from, imagine that I want to go from this top vertex to this right vertex, that means I need to pay a cost of 3. I don't know what is the 3. The 3 can be modeled in any costly thing. It can be money, road toll, right? You go there, you pay the highway price, you need to pay $3. Or you can treat it as time. From the top to the left, I need to spend 3 minutes or 3 hours. So all this number is a cost. All the main goal of shortest path algorithm is, I don't care how you define the cost, but shortest path algorithm can help you to find the lowest cost. Okay, so that is why shortest path algorithm is so useful. So here, we need this structure. We need a directed graph. We need a cost for each edge. So the question is, if you define one node as the source, how do you compute the shortest distance to every node? Okay. For example, can anyone try to see what is the shortest distance from S to D? Distance, I mean cost. Anyone is 2? Anyone is 4? Anyone say is 6? Yeah. Anyone is 7? Yeah. The answer is 6. Yeah, for those who think 7, maybe you say, oh, S go to here if a cost of 3 and go here as a cost of 7. But if you take a longer hope, that means S go to here 3 But take here, go to 1, and go here to 2, you only need 6. So that's by cost calculation, that is a shorter path. Also, the shortest path does not depend on how many edges you went through. You can went through so many edges, but the shortest path calculation based on the weight of the edge. We call it the weight or the cost of the edge. So this number 3, 4, 7, they are called the weight or the cost of that edge. So for example, this one, the shortest distance is following the red arrows. You may take more hoops. When we call hoops, we call how many arrows you went through. You may take more hoops, but it actually produces a lower cost. So the question is, what is the shortest distance from S to D? And also, what is the shortest path from S to every node? Of course, there was another big question is, what is the shortest path between every pair? But the last question we are not going to answer today. Why can't I just use breadth search? Yesterday, we say that breadth search can find shortest path. Why? Breadth search can only find the smallest number of hoops, not the smallest number in terms of the weighted distance. So if you use a breadth search, this will be the so-called double code shortest path, in which is not the lowest in the distance. So breadth search only find the minimum number of hoops. So we need to define one thing. We call it delta UV. Delta UV is so far the estimated distance from a node U to V. That means U and V can be any two nodes. Maybe let me ask, what is the distance from this node to this node? Okay, so that is a delta UV you want to define. And we call it the shortest distance, but before we start the algorithms, we do one following things. First of all, you know that you are starting from S, right? I will create something in the red box I call estimated distance. That means I guess first. I guess what is that distance first. But one thing you guess must be correct is, if you start from S, you go back to S, is 0 distance. Is okay? So I don't move, right? I start from here. Where is your distance? You come from here to here. No, right? No distance. So the distance from yourself to yourself is 0. And next, I take a guess. What is the distance from S to A, S to C, S to B? I want to say that this is from S to A. S to A means all the, I don't care what is the root, but if I want to come from S to C, I have a guess of what's the distance. And at the beginning, I guess also the distance is infinity. That is the starting of the algorithm. I guess if I need to go from S to A, I need infinity time. So every node actually has an estimated distance. Okay, now I need to, so one of the invariants in the whole algorithm is the estimated distance from S to any node will be always larger than or equal to the shortest distance. It makes sense, right? So my guess would be larger than the best. And now this is the one thing I say that everybody may not be easy to understand. So I take it very slowly. It's called relaxation of an edge. For every edge, I can do some relaxation. Let's see. Let's say you start from NUS, okay? Last time you start from NUS, and you know that you want to go to Geo Airport. And you know that before my estimated time, I don't care how you go there. I somehow, in the middle of calculation, I know that from my experience, I need to go from NUS to Geo Airport, use 60 minutes of time. Okay, that's what I knew. And now I want to add one information. I know that somehow I don't care how you go over there, okay? Maybe it's a bus, whatever. In NUS, I go to Expo, I need 50 minutes. Okay, this is just facts, okay? This is just facts and assumption. And now the question of this relaxation is, what if I find out there's a way from Expo to Geo Airport is 5 minutes? So the edge we want to talk about is this from Expo to Geo. Will that change my perspective how I go to Geo? Will that be? Will it change? Will this edge from Expo to Geo, will this improve my estimated distance to Geo? It will, right? Because I can actually go to Expo first, then I go to Geo, then I only need 55 minutes. So this edge improve my estimated distance to Geo. Then actually the destination decision is, should I change this? So for every edge, you know where you come from. So for every edge, this edge here, I want to do a relaxation on this edge. So what you did is, because I know this is 5 minutes, you have a destination of this edge, you have a sources of this edge. This is sources of this edge. Sources of the edge are not the sources of the whole overall. These are the sources of the destination. I can use this three piece of information to decide my sources, my destination, the edge destination, will it be improved? So in this case, what I will do is, because I know I can do 5 minutes from Expo to Geo, that means I can improve this estimated distance to 55. Okay? So that is how I improve it. What is the other case? The other case is, what if it's not the case like that? Okay, so the question is, do I want to take this edge? What if this is not 5 minutes? Actually, from Expo to Geo Airport, you actually need 50 minutes. Will you take the edge? No, right? Because you go to Expo is 50 minutes. You take from Expo to Geo Airport is 65 minutes. Does it improve? No, it doesn't. The original way, I don't care. You went from NUS to Geo, is good enough. You take the new route, you take more time. So you have two choices. One is, so you sum this together. You sum this together and see whether is it larger than or smaller than your original price you need to go to the. So that means if you have a new edge, you want to see whether this new route is better than the original estimated route. So this is what the relaxation is about. To abstract it, that means if you have all the nodes, remember that any nodes like A and C already have some estimated distance. And for example, I know that the estimated distance from S to A is 3. The estimated distance from S to C is 9. And now you want to do the relaxation on the edge AC. So now, what is the new estimated distance of C? 7, right? Because it's better. So what you do is, if you find out from this edge, I can go to A and go to C is better, I update it to be 7. So I'll update this guy to be 7. That is called relaxation. Of course, there's a chance that this is not 4, maybe this not 6, 6 cannot. This is 7. So 3 plus 7 become 10. That means if I go from here and then go from here, I need 10 minutes or $10, which is worse than original 9-1. So I don't update C. So this is what we call relaxation. Overall, if you graph, you want to relax. For example, if you see this, the first relaxation is, I want to relax this edge. Previously, this one is infinity, right? If you remember that I update everything to be infinity in the beginning of the algorithm, initialize it to be infinity. And now you know that from S is 0, S plus 3 will give a 3. That's why I can update A as 3. And now let's relax. Oh, this is what we relax SA. And now let's relax AC. AC here. So I know that actually when you relax AC, you only need to look at this part of the graph. S go to A, I know that it's 3. If I go to S, go to A, I use the HAC to go to C. What is the total distance? 7, right? And this is, if I go here, all the way, I need 7. And what was the original estimated distance for C? Infinity. Of course, 7 is better than infinity. That's why after I relax AC, I will got update C to 7. And so on. So you relax the edge. What is the next edge you want to relax? Let's relax AB. Relax AB, okay? So B originally is infinity. AB is, you take from the source of AB, which is 3, add 1. That's why we relax B to be 4. And now let's relax SB. B already estimated as 4, right? But now you propose, should I go from S to B using the HSB? Is it better? Should I take the new route, SB? No, because SB needs 5. And then B only is now, if I take it from S to A to B is 4 only, so I don't update B. And now let's relax BC. Okay, if I relax BC, you can see that the original estimated distance to C is 7. That means I don't care how did I come to that, but I knew that there was some way before from S to C is 7. And now when I relax this edge here, I know that B is 4. That means I also don't care how you end up in B, but I knew that S to B is 4. And now if I take this root all together, add this together is 6 only. That means my 6 is better than a 7. So that means I can update C to be 6. And so on. So this relaxation is getting an edge, and you compare your sources and destination estimated distance to decide what is your destination distance. And the shortest path algorithm in this Bellman plot is for every edge, let's relax that. But it's not a complete algorithm, huh? Does it work? For every edge I relax? The problem is it's only sometimes work. Why? How many times do I need to relax this graph? If you by visual, what is the shortest path from S to E? Just visual. You see that the shortest path from S to E is having a cost of 2, right? You go from S to D, D to E, right? But however, when I relax the edge, which edge should I relax first? Maybe the algorithm actually goes wrong. The edge order is I relax S, C, and then D, E. So I relax S, C to make SC to be 1 and relax CD to make D to be 10. And now I have an estimation of relaxing D will make the E estimated distance to be 11. And now I relax SP and DT, and then DE, I improve the estimated distance of E to 8. And now I estimate SA, AD, and DE, I improve the estimated distance of E to be 3. And now I estimate SD, and finally I have the last so-called estimated distance. But if you notice that I actually has to relax the edge DE many times. In this case, I relaxed the DE 4 times. I have to keep relaxing it. I mean, one edge, I need to repeat it, relaxing it. So this is Bellman. This is the real guy, very handsome, Richard Bellman. His Bellman for algorithm is quite simple. So the inner loop just now we do is here. For every edge in the graph, I relax. But I need to loop it n times. Okay, so I need to loop the thing n times. Why? Why do I need to do that? Because on the other example, do I have to really repeat n times? You can actually finish that means the loop, you can actually don't need to continue as to relax if further relaxation does not give you any improvement. That means your graph is already so-called a converge to a wireless solution. So your entire sequence of edge relaxation have no effect, then you can stop. This one, the yellow box. You can actually improve so-called terminate the first outer layer of for loop if there's no more improvement. So if that's so, what is the running time or where is the worst bound for Bellman fault? This should be easy. Who say 1? Who say 2? Who say 3? Who say 4? Who say 5? Yeah, 5, only 1. Why? Because you go to this loop, this is V and this E. So the answer is E times 3. Okay. And this Bellman fault. But the question is why? Actually, if you notice that Bellman fault, this is the why it works for n time is every time you relax after one iteration, every node within one hoop of jumping from the sources, the estimated distance is correct. After two hoop is correct, and so on. So after 3 hoops, with iteration, 3 hoops is correct. And that's why after 4 iteration, the destination D is correct. And if you have graph have n vertices, the longest path is n. That means after n iteration, your relaxation will be correct. So that's why Bellman fault here, if you loop it n times, will be correct. Maybe. Why maybe? Because what if your edge have negative weight? First of all, philosophically, what does that mean? For example, if I go to S to A, right? Let's say I pay $3, or I need to use 3 minutes. Then what does it mean by negative weight? What does it mean by I go to A to C then? For example, if you, let's say I go from S to A, I need to pay $3. Then go to A from C, that means what? I can gain $4. Okay. So for the cost, you can define positive is what you want to pay or you want to minimize. But some problems allows negative weight for some whatever reason. Okay. We don't care. We are mathematician and computer scientists. We just provide you a solution. How you model your graph is your problem. So some people will need to model your graph with negative weight. So for here, does it work? No problem. For Bellman fault, it works. Bellman fault can work with negative weight graph, except, how about this? Let's say you are the truck driver, okay? You have to pay the road toll. From S to A, you need to pay $3. But if you drive from A to C, you can gain $4. What will you do? Will you deliver your goods from S to C? I won't. I just keep the loops. I gain money. I keep driving from A to C to B, A to C to B, A to C to B, I gain money. And my so-called the total cost will be negative infinity. Because I can keep doing the loop and gain. So because your goal is find the minimal cost, right? Your minimal cost is as low as possible. The lower, the better. But now I can find a way and get my cost to be negative infinity. So the overall meta question is, if you have a graph with negative cycle, what does that mean? What does it mean if your graph have a negative cycle? That means your graph is either will fail with your infinite loop or you don't have any correct answer because your answer should be negative infinity. So the question is, if your graph have negative cycle, I'm not going to play with you. I'm not going to find you the shortest path because there's a meaningless question. But then, how do I detect a graph have negative cycle? That is where one of the Bellman fault strengths that Dijkstra cannot do. If you want to detect a negative cycle, that means, remember last time we say that for Bellman fault algorithms, after V iterations, you should be stabilized. You cannot improve the graph anymore. But if you run Bellman fault for more than V plus 1 cycle or V cycle, more than V cycles, you still can reduce the cost. Something is wrong. So you can actually run Bellman fault for V plus 1 cycle. If you can still improve the total weight, that means your graph has a negative cycle. So one of the biggest strengths for Bellman fault is you can use it to detect if the graph has a negative cycle. So there's some special case for Bellman fault. How do you find the shortest path if you know that every edge has the same weight? Do you still run Bellman fault? Well, you can still run the VE square, but if you know that all the paths having the same weight, that means the path length is actually directly proportional to how many hopes. If you remember our first mentioning about the shortest path, breadth first search actually can find you the path with the minimum hope. So if you know that all your paths have the same weight, you can actually no need to use Bellman fault, but directly use breadth first search, which is an extremely fast algorithm. Breadth first search only runs in V plus E time. Okay, so the basic idea for Bellman fault is I keep relaxing every edge for V iteration. I will stop when actually no more improvement. That means when it converge. And the basic idea for Bellman fault is V times E time. And Bellman fault has the ability, it can work with negative cycle. Oh, no, negative edges, negative weight edges. But if any graph actually have a negative weight cycle, on top of our problem, we actually reject this graph. We are not going to do it for you. It's nonsense, okay? But then how do we detect that? We can use Bellman fault to detect that. So today we talked about this Bellman fault algorithm. However, Bellman fault, you know that it's not very fast. It's VE time. The question is, how do we actually compute it faster? Okay, so that's it for today. That is the Bellman fault algorithms. And tomorrow, or not tomorrow, next week, we'll talk about Dijkstra. Dijkstra is a lot more interesting. Yeah, this is next week. Yeah, Dijkstra. Or not, this is not for us. Yeah. So no. Dijkstra. Okay, next week we'll talk about Dijkstra. Okay, so we still need to use the relaxation for Dijkstra. So if you didn't understand the relaxation edge, please repeat the video and look at it carefully. Thank you. That's all for today. No questions.